talking about these, some of the other sumo mechanisms here that we're going to end up seeing. And so we're talking about this halogenation reaction, right? Adding halogens across our double bonds. We said that if we do our halogenation, we end up seeing that three-membered ring intermediate there. And whenever you see that three-membered ring intermediate, that tells us some important things. Important things like there is no carbocation, right? It's going to be having partial positives, but there's not a full positive. If there's not a full positive, what does that mean? No shifts, no rearrangements, blah, 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 blah. Got it? It's going to behave pseudo-SN1-like. Okay? It does still have a partial positive. But part of the mechanism is SN2-like also, because it attacks the opposite side of whatever is leaving. Okay? That's what I need you guys to understand about this three-membered ring intermediate. Whenever you see this ring, and whenever we're going to react something with these rings, okay, we're going to have this play between which of the two carbons in the ring gets attacked, okay, and why. And we'll talk about it probably in the first chapter of OChem 2 is where we'll get back to this stuff again. How many of you guys are going on to OChem 2, by the way? You sure? I'm just kidding. Oof, got him in the stomach right now. I'm kidding. No. All right, so most of you guys are going to be in OChem 2 also. Okay, so we'll be picking this up. We'll be picking up some of these reactions in OChem 2 also, right? We'll talk about epoxides, and that we'll start out talking about epoxides. And they'll have the exact same mechanism here. And so I'm going to ask you guys on the first week of OChem 2, how do you think these things are going to react? And you guys are going to go, I don't know, Dr. H. We've never seen him before in our lives. But I'm showing you, okay? I am showing you the future. Okay? You guys are going to see this again. Right? The other part of the future that I see is you guys forgetting it. Don't forget it. Don't let my hours go to waste here. Okay, but all joking aside, remember the promise that I did make is that I wouldn't expect you guys to know a mechanism if you didn't see it applied in other cases. And this is going to be absolutely here. We're going to see this three-membered ring intermediate and them ring opening, right? We're going to see these ring opening reactions in multiple different situations, okay? So make sure that you guys understand how this works. Okay? It's a mix between SN1 and SN2. And so the first thing we're going to do today is the exact same thing. You guys ready for it? I'm going to ask you guys to predict the product. You sure you're ready? The confidence is just oozing out of everyone. Right? I'm going to ask you guys to do the exact same thing. So here's the exact same thing. Okay? There's some bromine, but now I'm going to put it in some water. Water is our solvent. Got it? So go to it. See what you guys come up with. You guys catch the important thing I told you though? What's water? Okay. Projector's going down. Might be opera time. Yeah, it looks fine. What? Don't use your book. That has the answers in it. No. Man, you guys trying to learn for free. Jeez. You did? Oh no. I'll have to show you guys ways of, only there were certain websites that like your mechanism, but think about what your product, think about what that means for your product. So I'd give you 9 out of 10, let me put it that way. Or another way of saying, I'll give you 10 out of 10, but you missed the bonus points. You're adding all this stuff to it. We're not doing that. Now ignore that. This is going to react with that double bond. What's that going to make? No. It might make that. Okay, let me back up. It'll make that as a minor product, right? So we've got to do a major product that happens along the way too. Yes, but don't add that other stuff. If I wanted you to do that, then I'd say, I'd give you some other kind of product for it. Right? So what do you think's gonna happen first here? Exact same thing, right, exact same to get to this point. Then something different's gonna happen. Dropping carbon. Don't go on the carbon diagram. So nothing changes. So I would say this will be your minor product. So think about what it means. Why would I tell you that something's a solvent? What implication does that have? Right? All right. So, if you notice, this is something we haven't seen before, right? Uh-oh, something we've never seen before. My response is to act like a turtle. What do turtles do when they have a situation that they've never been in before? They say, yeah, I'm gonna go hide in my shell. Right? I'm gonna just wait to see what happens. I'll wait this one out. I don't know, I'm not a turtle biologist. Is that what they do, right? They kind of just hide, right? Okay. But is that the response that we should have, though? Because I'm gonna give you a hint for all of life. That's really my job, to fix everyone's life, right? Ugh. Got a long way to go. Right? But remember, you're gonna be in situations that you've never been in before. When you're in that situation, after you're done panicking, what you need to do is go, well, what do I know? Right? What have I seen before? Right? We have an alkene. What's the only reactions that we know how to do with alkenes so far? Additions. So your first thought should be, I'm probably going to do an addition. Is that a bad thought? No. Okay, so what are we going to add? Are you going to add H2O? No. Have you ever seen an alkene add H2O? Yes, in the presence of an acid. Do we have an acid here? No. So we can add H2O if you have an acid, but we don't have one. So guess what you won't do here? Add H2O. Got it? Okay, so then I have to add my Br2. Have we ever seen an alkene add Br2? Yes, we have. Is it going to change? Is the mechanism for bromination going to change just because we're in water? No. Why does Br2 add? What's at play behind the scenes?
It's size.
That's part of it for sure. Here's what I'm asking you guys. The first step in this mechanism is going to look like this. Okay? The same as what we did before. Right? This is going to reach out, and that's going to do that. Right? We have this little weirdo three arrow mechanism. And at the end of the day, we do that. Ugh. You guys with me? I'm asking is, how does the solvent affect that step? Where's our solvent in that step? Do you guys see it? It's not there, so what does that probably mean? It's not affecting it, right? Why does that step happen? That's what I'm asking you. Why in the world does that happen?
Because it can't do anything else.
Maybe. How does all of organic chemistry work?
Positive to negative. Negative, positive.
Negative, positive. Okay? So the alkene is negative. Why is it hitting that bromine? Because the bromine is positive. Why? I don't see a positive. Why is it positive? It's all because of dispersion forces. Are dispersion forces influenced by solvent? The technical answer is yes. Right? But does it, for our purposes, it's not going to have that big an influence. Okay? The reason why the first step of this happens is because there is that dispersion force in the bromine that causes this to go. It's not influenced by our solvent. Do you guys get what I mean by this? What I'm saying is whenever you guys see Br2 and an alkene, you guys should think, I could do an addition reaction. Got it? So guess what's going to happen here in the first step? The addition reaction. And we make that what we call the bromonium intermediate, right? The three-membered ring with a bromine is a bromonium intermediate. Guess what we would call it if it has a chlorine? Chloronium, right? What if it had an iodine? Iodonium, got it? So that remember the IUM endings indicate a positive charge, right? Ammonium, right? One of your polyatomic ions, positive charge. Got it? Cool. So now we have that three-membered intermediate. As soon as you guys see that, what do you think?
The bond's gonna break.
Yeah. Whenever you guys see that three-membered ring intermediate, what should you guys be thinking? What mechanism? Your sumos, right? This stuff's going to start pulling to one side or the other. And when it pulls to one side or the other, it leaves behind what? A partial positive. And it's going to leave behind the partial positive where? On the most substituted carbon. Then the most substituted carbon is going to do what? Or what's going to happen to the most substituted carbon?
Incoming nucleophile.
An incoming what?
Nucleophile.
Oh, got it? Do you guys get what the next step's going to be? So draw it. An incoming nucleophile is going to ring open that bromonium intermediate. So show me what that is. Careful. Good, but think about what's going on here with this one. You got the general idea, but remember there's always some subtleties with this stuff. Nice. So remember, we always have to pay attention to that side with this type of thing. Here, this is the not the bromine. I would say that this is a minor amount. So why is this coming into attack that carbon? Correct, so there's a positive here and we need to find something negative, right? We need to find a nucleophile to do this, right? Remember I told you this is what? A solvent, right? What does that mean? Yes, but be careful when it's pulling in this direction. Okay? When you're drawing this, you're telling me you're leaving a positive button on here. Okay? You've got the right idea, but just be careful with what you're drawing. Okay.
Sorry. No. Don't worry, that's not.
Okay? So that's going to be the carbon that gets attacked by that, right? So show me the arrows for that. So that would be a minor carbon. Okay? Carbon diets. Carbon diets. So I would say that's a minor carbon, right? So this bromine comes in as a nucleophile, right? But what is it? When I told you this was your solvent, right? How have we seen water decay before? Right? Good, but be careful with this, right? So I give you 10 out of 10, but you missed the bonus points on the example. So think about what implications this mechanism has, right? Good. All right. So after we've reached our bromonium intermediate, right, if you said that a nucleophile is going to come in and hit the more substituted carbon, right? Well, what options do we have for a nucleophile? What options do we have for something that is, what is a nucleophile? What's a nucleophile?
On the hunt for something positive.
Huh?
On the hunt for something positive.
Why?
Alone together.
Yeah, right? It's something negative or partially negative on the hunt for something positive. It's got some nukes to file, right? So what nucleophiles do we have available?
Bromine and water.
Is the Br minus a nucleophile? Yeah, you bet, right? You bet. But I gave you guys some important information. What did I tell you? Water is your solvent. What does that mean? What does it mean to be a solvent?
There's a lot more of it.
It's there in the highest concentration. You guys got it? Can water act as a nucleophile? Yes. Is it a great nucleophile? No, but if you're there in the highest concentration, okay? If you're there in the highest concentration, guess what's going to happen? You're probably going to end up ring opening this bromonium intermediate here. Good. But we just gotta finish things off here. A little cleanup act. There it is. Good. What do we have to pay attention for in this reaction? Bromine's going to react first, create a bromonium intermediate, We generate that sumo mechanism, and the next step of the mechanism is what? So first step is make 3-membered ring. Second step is what? Open the ring with a nucleophile. What nucleophile? Any nucleophile. The best nucleophile. Is water the best nucleophile though? No, but what is it? What advantage does it have? It's a solvent, which means it's everywhere, right? It's solvating everything. So it's surrounding all this stuff. Got it? Could the bromine come in and still do that ring opening? You bet. Right? You bet. Bromine's a fantastic nucleophile, far better than water is. But why is that my major product? It's my major product because of what? The solvent is acting as a nucleophile, the thing with the highest concentration. We're playing a statistics game, right? That's what we're doing. Make sense? But I still have a mistake. What's my mistake? Yeah.
You need to add another bromine.
No, that's going to be a minor product, right? What's my mistake? It's a racemic mixture, right? Whenever you go through the sumo stuff, racemic mixture. I have to find my chiral carbon. Where's my chiral carbon? Right there, right? So my answer is the wedge, right? And I ran out of room. But I think you guys get the point. Okay, sorry, that sucked. Right? Chiral carbon, wedge and dash gets formed. Got it? What did I tell you guys about this? I'm telling you guys a lot of information, I know, and I'm not trying to pick on you guys or do anything, I'm just trying to drive the point home. I told you guys that this reaction is what? It's pseudo like an SN1, correct? And it's sort of like an SN2, correct? So what does that mean? Whenever you do an SN1 reaction, do we have to pay attention for racemic mixtures? Yes. This is sort of like an SN1, so guess what we should do? Pay attention to racemic mixtures. It's sort of like an SN2. What do we need to pay attention to in SN2? Sterics and the nucleophile. Do we have to pay attention to sterics and nucleophile here? You bet. Got it? So what do I expect you guys to pay attention to?
Everything.
Everything, good. You guys got it? Remember, we're always building evidence. We're building a case for which reaction happens. Have you guys started to notice that we keep asking the same questions though every time? Over and over and over? What changes though? Well, sometimes our answers change. Do we have a good nucleophile? Yes or no? What's our solvent? This or that, right? Is it a good nucleophile? Yes or no? How much of it's there? Yes or right? It's always the same set of questions. And if you guys can start to condense your questions down to ask good, relevant questions, then you guys can stop studying for organic chemistry, right? Because all you need to do is study your questions and then answer those. And if you answer those questions, you guys can figure out any mechanism. Promise, okay? But it's going to take time to get there. That's the advantage that you guys don't have, right? It's time. Right? We were, right? Fast, right? More. Okay? But that's how we should start approaching these types of problems. Not just like, oh, here's another mechanism, better memorize it. If this, then that. Good luck, right? That's a lot of stuff to memorize. Okay? But understanding makes life easier. At the end. It's hard at the beginning. I get it. Okay? I'm not arguing that. I'm not saying this stuff is simple. That's not what I'm saying at all. But what we need to start paying attention to is just how do we get to this answer? Can you guys explain to me the logic behind each of these steps? Right? Not just can you guys show me the steps again on the exam. Right? Can you guys understand the steps to get to the answer? Right? That's the question. Why would water want to come in anyway? Right? There's something else going on behind the scenes too, right? What's a stronger bond between a carbon and oxygen or a carbon and bromine? Carbon oxygen, right? So there's a steric argument, right? There's always an electronic argument. There's always a steric argument for something to happen. Cool, all right. There's Gen Chem stuff. You guys want to do this instead? No. No. All right. You guys want to do something easy? We demand more difficult things, Dr. H. All right. Okay. Always give me a second to think before I. Let's see, a really difficult one to make you guys think a lot. You guys do this. Okay, so come up with a method, a series of steps to go from one to the other. Okay. So use your knowledge. To make a useless molecule. Okay. What do you guys have? That's may do that, right? But then we have to worry about that. Sorry, I know the exam was online anyway, so I'm not gonna hear you. I'm just gonna send you guys like a PDF, right? There's students that are still out and stuff. So. Yeah, we don't have to worry about showing up to the lab or anything else. I'll give you guys 30 minutes to do it at home. Why are you guys laughing? Why? You guys want more time? Jeez. Fine, 35 minutes. No, I'm just gonna send you guys a PDF and you'll upload it, that kind of thing. But,
Is that for tomorrow?
yeah. Yeah. Maybe.
Wait, you're saying this?
Isn't it going on?
I'm saying it's gonna take more than one step.
Yeah, but it knows it's
In fact, this one's gonna take, at a minimum, 2 steps.
Yeah.
Does it matter which
Yes,
step we take first?
yes. What? You want me to judge harshly? Oh, man. You call that a synthesis? No, that's fine. That's good. See if you can come up with a, yeah, I guess there's only one way we can do this. No, that's fine. Good.
For these subjects, so we need to show the mechanism of
Sure. Yep, sounds good. Be good practice, wouldn't it? No. I'm gonna disagree with you. Oh. That's not right at all. What are you doing? Got the right idea, but the wrong tool to do the job.
So it's the
If you do that, if you use that base with what you had, you would not make this. You'd make something else bigger. Right? You'd make the more substituted one. Right? So you gotta do, so like I said, that's what I mean. You got the right idea, but use a different tool to get it done, right? Hmm? What's that? Why don't you try that as a panel? Always a good place, right? Yep. Well, I'll tell you guys here in a second, but. So, whenever we have a problem like this, what's always the most important thing you guys can do in life? Stop and think. What do we see in our product? We have a OH that's next door to a bromine. How many reactions have we learned to put a Br next to an OH? 1, right? The name of that is the, where's my, right? So if I'm going in reverse, I'll draw it in red, right? So if I'm going in reverse, I had to have started from this double bond. You guys with me on this? And if I have that double bond and I add Br2 and water, right? Then I make my product. You guys following along? Does everybody see this? How do I know that my double bond had to be there? Because in my reaction, the OH gets added to the more substituted side. Okay? Now I have to make an alkene. Can I make an alkene from where I started? Yeah. How can I do that? How can I? Well, I need some bulky base, right? So my T-butoxide, T-butanol. Okay. Start from something identifiable. The OH next to the bromine, there's only one reaction we know how to do that. has to mean that it comes from an alkene before that. And then it just becomes make an alkene from an alkyl halide. Good? Yep.
So we're just backtracking it?
Yep.
Okay.
What we call it is retrosynthetic analysis is what they call it in the book. Sounds really cool, huh? It just says, which basically it means think. Work it in reverse. What did I have to have before this step? And keep working backwards until you get to your product. Okay? Does it mean this is the only answer to get to this? No. Is this the best way to do it? Yeah. How do you guys know this is the best way to do it? I told you, right? What's the best way to do this? Whatever you guys have right now, right? I didn't ask you guys make the most efficient synthesis at the highest yield, blah, 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 blah. Okay? If I did that, then we'd have to come up with multiple ways and assess and do all that kind of stuff. I might ask you that because I'm a jerk, right? Why are you laughing? Who's laughing? Right? And then we might have to come up with multiple ways of doing this. Okay? But if I just said, just make that there, you're like, okay, then I get to use whatever tools that I have in my toolbox to make it. Okay? It's just a puzzle. That's all it is. Good. You guys want a difficult one to think about? Let me think here for a second. Sorry, I gotta come up with stuff on the fly. Okay. Give me just a second here to think for a minute. Okay, yeah. Go ahead and see what you guys can come up with a way of doing this. Right? It's going to take a couple of steps to get there. Nope. You can see similar setups, right? You're going to see very similar parts to it, right? But there's going to be some important things along the way. No clue. I would disagree with that.
Try to do a substitution.
Probably, maybe, potentially. More than one way to skin a cat, as they say. Figure it out. Okay, what would that be? If you had to reform, would that be your call, or the top? Now you even make an alkene. How can you make an alkene? What do you have to function to get that purpose? What are the only reactions that we know that can make alkenes? Eliminations, right? To do an elimination, but you have to have some kind of leaving group, right? So you have to put a leaving group on one of those two carbons. No. That seems reasonable. That's fine. What else could we really do in this case, right? So, now we're done. I can get my head in this next little bit. Okay, so working in reverse, we see the same thing here, right? So we know that we have to come from that, right? How do I make an alkene? What are the only reactions that we know how to make alkenes? Eliminations. To do an elimination, it means my leaving group had to have been on one of those black carbons. Got it? You guys follow along with this line of thought here? To do an elimination, to make that alkene, I have to have my leaving group on one of those black carbons. So I'm going to put a leaving group on one of those black carbons. Got it? Let's see, am I where I started yet? No, but I'm getting a little bit closer, right? So how can I put, right, how can I put that bromine on that carbon? So see what you guys can come up with. I've narrowed it down for you guys a little bit here. It's still going to take more than one step. Okay? If you don't know, is that what you said? You guys know. All of you guys know. I promise this isn't all of your guys' notes. all the answers.
Does it have to be bromine, or could it be bromine?
And you can do something else, yeah, sure. What leading group do you want there, so? Okay, go for it then, do that. I agree with this. I think that's fine, but that's not gonna do this. Hmm?
On that side.
It might, depending on what you want to do, right? There's different ways to do it. So that's the whole point of this exercise, right? You have an idea, follow your idea. Does it lead you back to the beginning, right? There are more than one way, there's multiple ways of doing this. I think you do, but you've seen the problem, and I've given you two of the tools to fix that problem. So now you just have to find the right tools in your toolbox, right? That's what you're saying. Got it? So let's think. Can I do a direct substitution? Can I go directly from the beginning to my compound in blackface? No. Okay? If I do a substitution here, right? I'm walking through my different options. I have this molecule. What can I react with it? Could I do an elimination? Sure, right? If we do an elimination, we can get to here, right? We know that that's the one, oh, I forgot to fill it in there. I'm a dum-dum, right? So let's LDA it up. Oh yeah, LDA, all right, okay? All right, so if we do an elimination, we can get to this product here. Good? If I substitute, what's gonna happen? Well, I just switch something in place of my bromine. Is that gonna help us? Maybe not, right? So how can I add a bromine? Oh, maybe I need to do an addition reaction. Which means to get to there, right? Can we go from green to pink? So here, the best we could do is some kind of strong base, okay? How do I do my reaction in pink though? Where is my bromine going to be added to the less substituted side? So I can't use an acid. Why? Because an acid would form a carbocation. And form a carbocation is going to shift and rearrange. So I have to add a Br to the less substituted side. How many reactions do we know that does that? One. Right? HBr peroxides. Good? Take a look at what we did here. What's the step in blue? Elimination, addition. Elimination, addition. You guys get what we're doing here? Eliminations followed by additions. Eliminations followed by additions. There's only 3 reactions that you guys know how to do. Did you guys know that? You can either substitute, you can eliminate, or you guys can add. You guys catch that? For each of these steps, all you have to do is think, which of those 3 reactions can I do? So at most, you guys only have 3 options at each step. You can either eliminate, you can add, or you can substitute. Got it?
What's the mechanism for the purple one? 'Cause I don't remember.
Right. We will learn that in a couple lectures. It's in the next. It's in a chapter that's not in this exam, but we'll learn it. Yep.
In the first step,
Yep.
wouldn't it make like 3?
Yes, it would. But make a big mess, right?
Is there a way that we can do it to be sure that it will make one that?
Not in the methods that we currently have. That's the best we can do. Right? We pick a reaction that'll take us to our product. Right? Any of those 3 eliminations would be considered a major product. Right? So we just say, well, we do the best we can. Right? So that's a good observation. Cool. I can tell you guys thoroughly enjoy this. Are you guys going to be seeing some of these multi-step things? Yes. Okay. We have to start using things in logical sequence. This is why I'm telling you guys, you only have to, listen, I hope you guys are starting to understand how I try and teach you guys things, okay? The way my approach is, there's too damn much information. I don't remember all this stuff, and I do this every day, okay? I'm just kidding, I remember. No, I'm joking, I don't, right? But what can I remember? I can remember 3 things. My 3 things are what? Substitutions, eliminations, or additions. My goal for you guys, the way I try to tell you guys what to do, is always trying to get you to a fork in the road. And if you've noticed, our answers usually always come down to, we have 2 options. And what do? Well, we follow both options, right? And we say, this led us to something useful, this didn't, okay? This one's a little bit more tricky because now we end up always at what? 3 options. But guess what we could do? Follow all 3 options, and one of them has to get you to your answer. In fact, sometimes multiple could get you to your answer, okay? That's the beauty of these things here. This is not the only way to do this problem. Could you guys think of another way of doing it? That'd be good practice, right? But there's multiple ways of doing it, which is great. These are the types of exam questions you guys want. Why? Because there's not a right answer to that, right? There's better answers, there's elegant answers, but I didn't say that. I didn't say give me the most elegant answer. I said just give me an answer. Good? Right? All right, so for the exam, look online tomorrow. We'll open it up early in the morning and give you guys kind of all day to go through it. I'll give you guys the instructions in there. Expect it to be somewhat similar to what you guys have seen in the past. And then just make sure you guys upload your stuff, with all your work and everything, okay? Yeah.
Is it open book?
Is it open book? What do you guys want? Yeah, okay. Don't ever ask for open book exams, they're always harder. Okay? Because I know what's in the book. I'm not gonna ask stuff from the book then, I gotta make up my own questions. All right.
I mean, like, can we look at our notes or not?
Huh?
Can we look at our notes or something?
Sure, go for it. I don't care, right? Yeah, that's fine. You guys can do, what we'll say is this, right? It's open book, open note, but what do I expect you guys to be doing? I expect you guys to work on your exam. I'll be very honest with you guys about this, okay? It is super easy to tell when people decide to combine their efforts, let's say, okay? It's really not hard to tell, because especially when I give a problem like this where there's multiple answers, okay? Promise, I've been doing this long enough, it's easy to spot these red flags and say, I know exactly what happened there, okay? So I don't care, use your notes, take your time, come up with a meaningful answer, but what do I want? Your answers. I want to see how you guys are doing, okay? I'll be around tomorrow, you guys can come and ask me questions. You can even come ask me the question of, hey, Dr. Ace, does this look okay? Right? And I'll go, whoa, right? Okay? I'm here to help you guys out. Good. So take a look for that. It'll be up tomorrow. And just get it done. You guys don't have to come sit on the stupid benches in the lab. Doesn't that sound appealing?
Just do it at the end of the day.
Yeah, we'll make it to like 6 or something or
You
something.
just submit it online.
Yep. You guys will just upload like a PDF or whatever. Sound good? Cool. All right. I will see you guys on Friday, if not before then.